Welcome to our presentation on multi-constellation satellite signal characterization near the northern crest of equatorial ionization anomaly EIA by Kalyan Chatterjee, Arundhati Sen, Abhranila. We'll now move on to our presentation. An outline of the presentation. Introduction. Satellite navigation. GNSS, GPS, ionosphere, Galileo, scintillation, carrier to noise ratio, objective of the experiment, proposed method, experimental setup, experimental results, result analysis, acknowledgement, references, and conclusion. Introduction. Satellite-based navigation and communication systems are of immense importance these days. In addition with their usual operational outcomes, many important atmospheric rather ionospheric characterization can be done with the help of satellite signals. In this purpose, many trans-ionospheric satellite links, that is GPS, GLONASS, etc. are commonly used. Such characterization of the ionosphere is very important for aviation and space research community. Satellite navigation. A satellite navigation or sat-nav system is a system of satellites that provide autonomous geospatial positioning with global coverage. It allows small electronic receivers to determine their location, longitude, latitude, and altitude elevation to high precision within a few meters, using time signals transmitted along a line of sight by radio from satellites. The signals also allow electronic receivers to calculate the local current time to high precision, which allows time synchronization. A satellite navigation system with a global coverage may be termed as a Global Navigation Satellite System, GNSS. Global Navigation Satellite System, GNSS, is a satellite system that is used to pinpoint the geographic location of a user's receiver anywhere in the world. Two GNSS systems are currently in operation: the United States Global Positioning System, GPS, and the Russian Federation's Global Orbiting Navigation Satellite System, GLONASS. A third, Europe's Galileo, is slated to reach full operational capacity in 2008. Each of the GNSS systems employs a constellation of orbiting satellites working in conjunction with a network of ground stations. GNSS signal. The GNSS signal at the receiver can be expressed as the formula given, where E is the normal received signal without scintillation or adverse ionospheric conditions, and delta E is the change in the received signal due to adverse ionospheric conditions or ionospheric scintillations. Ionosphere. The ionosphere is a part of Earth's upper atmosphere between 80 to about 600 km, where extreme ultraviolet and extrasolar radiation ionizes the atoms and molecules, thus creating a layer of electrons. The ionosphere is important because it reflects and modifies radio waves used for communication and navigation. Other phenomena such as energetic charged particles and cosmic rays also have an ionizing effect and can contribute to the ionosphere. Scintillation. What is ionospheric scintillation? Ionospheric scintillation is a rapid fluctuation of radio frequency signal phase or amplitude generated as a signal passes through the ionosphere. Scintillation occurs when a radio frequency signal in the form of a plane wave traverses a region of small-scale irregularities in electron density. The irregularities cause small-scale fluctuations in refractive index and subsequent differential diffraction, scattering of the plane wave, producing phase variation along the phase front of the signal. As the signal propagation continues after passing through the region of irregularities, phase and amplitude scintillation develops through interference of multiple scattered signals. You can now see the scattering, that is scintillation process. When and where does ionospheric scintillation occur? Scintillation is caused by small-scale fluctuation in the refractive index of the ionospheric medium, which is inhomogeneities in the ionospheric medium, are produced by a wide range of phenomena, example plasma bubbles, and those responsible for scintillation occur predominantly in the F layer of the ionosphere at altitude between 200 to 2000 km. The primary disturbance region, however, is typically in the F region between 250 and 400 km. E-layer irregularities such as sporadic E and aureole E can also produce scintillation, but their effect on L-band GPS signals is minimal. Ionospheric scintillation is primarily an equatorial and high altitude ionosphere phenomena, although it can and does occur at lower intensity at all latitudes. What is the impact of ionospheric scintillation? Ionosphere scintillation affects in trans-ionospheric radio signals up to a few gigahertz in frequency, and as such can have determinal impacts on satellite-based communication and navigation systems such as GPS-based systems, and also on scientific instruments requiring observations of trans-ionospheric radio signals, example radio astronomy. Amplitude scintillation directly affects the signal to noise ratio CNO of the signals in GPS receiver, as well as the noise levels in code and phase measurements. Amplitude scintillation can be sufficiently severe that the GPS signal intensity from a given satellite drops below the receiver's tracking threshold, causing loss of lock on the satellite and hence need to reacquire the GPS signal. This results in reduced accuracy, navigation solutions, data loss, and cycle slips. The nominal CNO for the LI signal is about 45 decibel hertz, and tracking may be lost when the signal drops below 25 decibel hertz, dependent on the receiver's specific tracking loop. These are some scintillation diagrams. Carrier to noise ratio. In communications, the carrier to noise ratio, often written CNR or CN, is a measure of received carrier strength relative to the strength of received noise. High CN ratios provide better quality of reception and generally higher communications accuracy and reliability than low CN ratios. Engineers specify the CN ratio in decibels between the power in the carrier of the desired signals and the total received noise power. If the incoming carrier strength in microwatts is Pc and the noise level also in microwatts is Pn, then the carrier to noise ratio Cn in decibels is given by the formula Cn equal to 10 log base 10 Pc by Pn. Under adverse ionospheric conditions, satellite-based navigation system completely fails and it poses an immense threat to high dynamic platforms such as aircraft that rely heavily on satellite-based navigation systems. Objective of the experiment. In this paper, the authors tried to investigate carrier-to-noise ratio fluctuations for GPS and GLONASS satellite links tracked from Calcutta during October 2013 to April 2014. By doing so, authors proposed the possibility of application of spatial diversity techniques under adverse ionospheric conditions to prevent scintillation process. Proposed method. In this paper, the authors have proposed a novel technique in order to analyze the carrier-to-noise ratio CNO fluctuations for GPS, GLONASS, and Galileo satellite links. Carrier-to-noise ratio as a function of time is contaminated by spatial changes between the receiver and the satellite. Two parameters have been driven to eliminate slow fluctuations arising due to spatial variations. First, 10-minute moving average of carrier to noise ratio (CNO) values separately for GPS, GLONASS and Galileo satellite links. Second, deviation of instantaneous carrier to noise ratio values from moving average carrier to noise ratio values. The fluctuation of carrier to noise ratio values lie between 0 dBHz to 12 dBHz. This range has been subdivided into three regions: low fluctuation region less than 4 dBHz, moderate fluctuation region between 4 to 8 dBHz, and intense fluctuation region more than 8 dBHz. Finally, polar plot has been generated which shows fluctuation of carrier to noise ratio values for different regions of the sky. The experimental setup operated at RPE, Calcutta during October 2013 to April 2014. Experimental results. You can see there are three plots, polar plots of spatial distribution of fluctuations of CNO for GPS satellite, the first one, second for GLONASS satellite, and third for Galileo satellite, all on 15th of February 2014, 8 to 12 UT. Now you can see in the left a polar plot of spatial distribution of fluctuation of CNO for GNSS, that is GPS, GLONASS and Galileo combined satellite links observed from Kolkata on 15th of February 2014 between 8 to 12 UT. Next, in the right, you see a plot of number of GNSS satellites tracked as a function of UT on 15th of February 2014. Result analysis. Carrier to noise ratio fluctuated due to adverse ionospheric conditions throughout the day, but most intense fluctuations noted between 8 to 12 UT on 15th of February 2014 from a ground-based receiving station at RPE, University of Calcutta. The amount of fluctuation is different for different constellations, such as GPS, GLONASS, Galileo, as is evident from the figure 1. Figure 2 shows the combined scenario of the carrier to noise ratio fluctuations. In a single day, at any time, 10 to 15 GNSS satellites can be tracked from Kolkata. So, under adverse ionospheric conditions, choosing right satellite becomes easier. Conclusion. A GPS-only receiver can track only 8 to 10 satellites at a particular time, but the use of a multi-constellation, multi-frequency GNSS receiver can track up to 20 to 25 satellites at any instant. This improves the positional geometry and accuracy of navigational solution, which is very essential for high dynamic platforms such as aircraft or moving trains, etc. In a geophysically sensitive location like Calcutta, irregularities in ionospheric electron density distribution, plasma bubbles, develop in the daytime due to solar activities. Scintillation takes place when satellite links pass through these bubbles. As a result, high signal fluctuation can be observed. Large carrier to noise ratio fluctuation can degrade the performance of navigation system, which may lead to catastrophic effects in case of high dynamic platforms. Intense signal fluctuations occurred in the north under the overheads of the station due to fountain effect in the south near the 150 elevation marks due to field alliance irregularities. Less dense configuration for Galileo satellites indicate very few Galileo satellites tracked from Calcutta during this period. Denser configuration in GNSS plot suggests the possibility of application of spatial diversity techniques under adverse ionospheric conditions in order to maintain good quality of service and to provide accurate navigational solution. Acknowledgement. The authors would like to express sincere gratitude towards all the people involved in Institute of Engineering and Management for their sincere help and encouragement. The authors would like to thank Dr. Ashik Pal, Associate Professor, University of Calcutta, for providing the satellite signals. Our references: thank you for watching our presentation. I hope you enjoyed this.